Just dancing with my eyes closed.
Now, some of you ask me, so what's the general approach? Should, in case, your teachers actually ask you, so how do you explain the solubility of a substance based on its bonding and its structure? Well, my take on it has been very clear right from the previous video. You only need to know. It's very difficult for you to explain because you do not understand all the kinds of interaction between the solute and the solvent, which is basically the idea behind solubility, isn't it? So therefore, we just need you to know the solubility generally, but we do not need you to know why. So I hope you can be comfortable with that. Now, let's clean up the act and then we just finish off with this whole last summary of things. Okay? Now, the last property that I'd like to do a quick summary to teach all of you how to answer, right, is this. Melting boiling point. That one is one long story. Okay, so if we're dealing with generally explaining melting boiling points of substances, people, even if you didn't know, you could use certain signs to teach you, right? Okay, so if a substance is solid state at RTP, you don't even have to ask, it's high melting boiling point, all right? If a substance is liquid state or gaseous state at RTP, then without fail, you will just classify it under low melting boiling points, all right? So that's generally it. Now, if you ended up with something that's low melting boiling point, the explanation is actually very clear. Number one, small structure. That means it must have simple molecular structure. And simple molecular structure without fail almost always would be made from small covalent molecules. They're neutral, they have weak intermolecular forces of attraction, so therefore it's not going to take too much to get all of them like far away from each other, or at least moving freely amongst each other without being held by strong forces in fixed position, right? So if that's the case, then that's the reason why they have low melting, low boiling point, okay? Now, for all those other stuff, which is the vast majority of it, they are actually solid state at RTP. That means, without fail, they must have big structures, or else they will not be big enough for you to see and to handle and be in solid state at RTP. So given that, then you have to analyze, okay, given this substance, what kind of particles make it up, and therefore you arrive at a conclusion about it. So if we are talking about compounds, right, then we will be talking about the giant lattice structure, and then the strong electrostatic forces of attraction between the oppositely charged ions, all that. So mention large structure, opposite charges, strong forces holding all of them in this large structure. So a lot of heat required to overcome all these things in order to melt, hence high melting boiling point. All right, so the same thing will occur for, let's say, if you think about metals. It doesn't really matter whether it's metal pure or metal alloy, solid state at RTP, so must be high melting boiling point. Then think about the metallic structure. What about it that makes it so strong? Well, the very mobile sea of delocalized valence electrons. They move freely. They're all negatively charged. They attract and they hold the metallic cations in fixed positions. If you want to melt a piece of metal, you have to overcome all that. So a lot of heat is required. Then your metal has a chance to melt. Therefore, guess what? High melting boiling point. All right. And then lastly, we talk about things like the macromolecular covalent substances like diamond and graphite. These are actually quite easy to explain. They are all giant structures, okay? Diamond has a macromolecular tetrahedral structure, and all through it is all strong covalent bonds. So you want to melt diamond, you have to overcome all the strong covalent bonds. Which part of it looks like it requires a little bit of heat? No, it requires a lot of heat. So therefore, high melting boiling point for diamond. Now, of course, then we have the last thing, which will be our graphite. Graphite is not much smaller than diamond. The only thing is in between layers of graphite. You do have those, Van der Waals forces, not quite strong, but when you look at each layer, no weaknesses there, okay? Every single thing is held to other things via strong covalent bonds. So yet again, if you wanted to melt graphite, you will have to overcome every single one of these bonds. So you really do require a lot of energy, and therefore High melting boiling point. So as you can see, I'm very, very consistent in the way that I'm approaching explanation for all the properties based on structure, based on bonding, and you must analyze the properties exactly as they are. Do not talk in general, talk specifics. Okay, when you're specifically explaining a particular property, you will normally get your point across very nicely. All right, do practice this so that you know all the keywords that you need to make your argument convincing. Okay, so if you like what you hear and you understand what I say, please hit the like button, and I hope you subscribe to my channel so that I can update you when we post out new videos. Right, happy learning!